In this lesson, we're going to look at the current as a function of time moving through the inductor. Now, we solved our differential equation. We have our expression for the current as a function of time. We note that the bracketed term represents the decimal percent that we are to maximum current, steady state current. The maximum current, that steady state current, is based on Ohm's law, so it's the battery voltage divided by the resistance. And here we can see our graphical representation, and it should look familiar to us mathematically from our charging the capacitor. The charge on the capacitor as a function of time behaved mathematically identical in functionality. Now, to understand our bracketed term, that percent that we are to the steady state I max, we'll go back and revisit our understanding of the time constant, and the best way, I think, to understand the time constant is to put an actual time to it. So that is why I chose the example here, simply using 2 Henry inductor, a 1 ohm resistor in front of it. So we have 2 seconds represents the time constant. So it's an actual time. So what is the circuit doing at t equals 2 seconds when we have 1 time constant? Well, as we saw from capacitance, that means our bracketed term is going to be 1 minus e to the minus 1, or 0.63. We are roughly 2/3 to our maximum steady state value. The fact that we see a slowly or more slowly growing current with the inductor than we would see without the inductor is the Faraday's law, resisting the time rate of change of the flux in the solenoid. Now, note, without the solenoid, theoretically, the current is not impeded, and we would go right to our steady state value. But that will never occur. There will always be some self-impedance in a circuit to keep it from going that quickly to the top. So now that we have our understanding of the endpoints, we can see that our function does match our endpoints right at time t equals 0. The induced voltage spikes, matches the battery voltage, and shuts down the current. So that's why we have 0 current down here. And at time t equals infinity, we never quite get there, but essentially we are at our steady state I max value based on Ohm's law. Well, the voltage across the resistor is very easy to understand because of Ohm's law. We have V equals IR, so our I function from above is the current that we use because the resistor is in series with the inductor, and we get mathematically identical functionality for the voltage across the resistor. And the last thing we need to look at then is the voltage across the inductor. Now, the voltage across the inductor, we have a couple of things here to note. One, we are assuming that there is no resistance to the inductor, and that certainly is not a very real-world approximation to make, because those wire the wire windings that we have certainly will have a resistance to them. But as a first order calculation, we are going to neglect the resistance of the inductor. Now, we know that the back voltage, the induced voltage from the inductor, is based on L di dt. The current is the same current we have been using. I've kind of shortened it here, though, a little bit for us because of the constant. So basically, when we take the derivative of our current function here, what I have done is brought the voltage divided by R in, and when we do that, we're going to take the derivative of a constant is 0, so I left that off in the interest of saving space on my paper, and just use the minus e to the minus t on tau. So I factored it in, brought it back in, and then now I'm taking the derivative. So when we take the derivative of e to the u is e to the u du. So here is our e to the u. this is our du, right? -1 on tau. Tau is L on R, so as you see here, we lose the L, we lose the R, and we get our expression down here for the voltage across the inductor. And again, that matches what we know is occurring based on our endpoint analysis. We have that the battery voltage, right, is matched by the inductor to shut down the current, and then the back voltage that is impeding the flow of the current through the branch of the circuit that has the inductor dies off exponentially, so it's exponential decay. Our time constant now represents not 63% full, but a loss of 63% of the voltage. So we've gone down 0.63 to 0.37, about 1/3 of the voltage after one time constant. So hopefully this looks familiar to you based on what we did with capacitance. I'll zoom back out here to let you get down the annotations that you need, and we will be moving on with the RL circuit.